Well, I'm gonna get started. This is spot. So, the second chapter 3 homework is due on the 15th. The quiz on chapter 3 was today in SI. The chapter 4 homework is due on the 29th. The quiz on chapter 4 will be on the 27th. So, a quick review. Work is force in the direction of movement times the distance over which you move. Kinetic energy is the energy stored in motion. So energy kinetic, that is 1/2 mass times velocity squared. And the work energy theorem says that work equals change in kinetic energy. So that's 1/2 mass velocity 2 squared minus 1/2 mass velocity 1 squared. Or final and initial. I have it written as final and initial here. So that's our quick review of kinetic energy and work. Now, potential energy is energy that is stored in the position of an object. So you get potential energy when you work against a force where you can get that energy back. So the most common form of potential energy you're going to run into is due to gravity. And that's the only one we're going to cover in this class. So if you have a mass, if I raise this mass up, I put energy into it because I have to work against its weight. And I can get that energy back by letting it fall. I'm not going to actually let it fall. So since the work I do against gravity is force times distance, weight is a force, mg. If we substitute height for distance, gravitational potential energy is mass times g times h. And you can measure the h from anywhere. You can set your h that you measure from wherever is convenient. So if I was doing a problem where I was lifting things above this table, I would set my 0 for h at the top of the table. But if I was doing a problem where I was dropping things to the floor, I would probably set my 0 for h at the floor. But I wouldn't set my h at the ground outside. That's what I might use if I was dropping things out the window. So, and there are other situations where you might want to choose strange positions for your h because it makes the math easy. So the gravitational potential energy is equal to the work done and thus equal to the weight times the height. So how much work is done lifting a 1 kilogram book to a height of 1 meter? So that work is going to be mass 1 kilogram times g 9.8 meters per second squared times the height 1 meter or 9.8 joules. So this is the amount of potential energy that the book gains by being raised a height of 1 meter. So the potential energy would have at a height of 1 meter. Now, potential energy, the nice thing about potential energy is that it is independent of path. It only depends on where you start and where you end. So your change of potential energy will only depend on the difference in height. It is independent of path. So if you disregard frictional loss, it will take the same amount of work to lift this mass m, no matter what path you take. You can lift it straight up, you can lift it at an angle. and so on. It'll take the same amount of work. Or when you're moving it at an angle like this, basically what happens is the distance is increased, but the force you're applying in the direction of motion is also decreased, and it balances out if you work out the force from the work another way. But it ends up being independent of path. So work is equal. So you can think of work as change in energy. It's energy moving around. So here we can think of work being the change in potential energy. So in the previous examples, height was actually change in height. So work is done when there is a change in position. Therefore, the reference point for measuring heights is arbitrary, but you do have to be consistent with it. You could choose anywhere as your reference point, but you have to be consistent with it. So you could measure from the ground, you could measure from the top of the table, you could measure from a distance infinitely far away, which is actually convenient sometimes. There's a lot of options. So here is an example showing putting 0 in the middle here at the second height, or putting 0 at the bottom. The change in height from the bottom to the top is still 100, whether you start at -50 and go to +50, or whether you go from 0 to 100. Change in height is the same. There's other places we can store potential energy. The most common one you're going to run into, springs. Elastic potential energy stored in the bending of a spring or the compression or stretching of a spring. With a bow, you can have some elastic energy in the stretching of the bowstring, but the primary thing with a bow and arrow is the bending of the limbs of the bow. That's where the energy is stored. Bowstrings don't actually stretch that much. So the limbs bend. If the bowstring stretched, you'd have a slingshot and not a bow. So here, if we have a 2-kilogram block that is raised a distance of 2.5 meters, how much will its potential energy increase? Remember, potential energy is mgh. G is 9.8 meters per second. We have a 2-kilogram block raised 2.5 meters. So 2 kilogram block weighs 2.5 meters. Potential energy is mgh. So 2 kilograms times 9.8 meters per second squared times 2.5 meters gives us 49 joules. Potential energy is an energy, so the unit is still joules. If I change the potential energy of a 4 kilogram block by minus 49 joules, how far do I lower the block? So here we have a block with a mass of 4 kilograms. We want to reduce its potential energy by 49 joules. We want to subtract 49 joules from its potential energy. So change in potential energy equals mass times g times change in height. Thus, change in height is going to be change in potential energy over mg. So minus 49 joules over 4 kilograms times 9.8 meters per second squared. So the change in height is negative 1.25 meters. I lower the block 1.25 meters. So it requires 147 joules of work to raise a block by 10 meters. What's the mass of this block? So potential energy is mgh. Mass is going to be potential energy over gh. So mass is going to be 147 joules divided by 9.8 meters per second squared times 10 meters, or 1.5 kilograms. So if I move a 2.5 kilogram mass from y equals minus 6.5 meters to y equals plus 9.5 meters, what is the change in potential energy of this mass? So potential energy is change in potential energy is mgh final minus mgh initial. Which is mg times change in height, h final minus h initial. So 2.5 kilograms times 9.8 meters per second squared times the quantity 9.5 meters minus negative 6.5 meters, which comes out to 24.5 newtons times 16 meters. You're subtracting a negative number, which is the same as adding. And so 392 joules. Any questions? Okay. So one of the most useful tools that you can do with energy is that, like momentum, energy is conserved. So energy can either be created or destroyed. And in changing from one form to another, it's always conserved. So the total energy of an isolated system remains constant, i.e., total energy at time 1 equals total energy at time 2. So the total energy will not change with time. This gives us a very helpful relation. If we don't have any energy loss to things like friction and other stuff, we will deal with ideal systems that only have kinetic and potential energy. You can have other forms of energy, of course. But what you get, this is the wrong marker to use, is energy kinetic 1 plus energy potential 1 equals energy kinetic 2 plus energy potential 2. Kinetic energy plus potential energy remains constant. You'll have energy changing from potential to kinetic and back, but the total remains constant. So that'll be 1/2 mv1 squared plus 1 plus mgh1 equals 1/2 mv2 squared plus mgh2. So as an example, you have a pendulum like, I'm put a big math on it. Hopefully they'll have less friction or last longer. So if I have a pendulum like this, and I let it swing, it starts with potential energy. At the bottom of the swing, it's kinetic, and then it changes steadily back and forth. This actually has a lot of friction. I get better results with the smaller mass. That might be the way I was holding it. Starts with potential. It's kinetic at the bottom and potential at either side. Potential, kinetic, potential, kinetic, potential, kinetic. This isn't long enough to be nice and slow. Pendulum speed is based on the length of the string, basically. So, an example, if you have a 0.1 kilogram stone that's dropped from a height of 10 meters, and you want to find the potential and kinetic energies of the stone at the heights indicated in the figure, neglecting air resistance, so 10 meters, 7 meters, 3 meters, 0 meters. We know that the total energy will be the same for all heights. So total energy equals kinetic energy plus potential energy. At the moment the stone is released, it only has potential energy. Kinetic energy is 0. And at the moment it hits the ground, potential energy is 0, and it's all kinetic. This is similar to what we're going to be doing in the lab. So at any height, we can calculate the potential energy. It's mgh. So at our first height, 10 meters, potential energy is 0.1 kilograms times 9.8 meters per second times 10 meters. It's 9.8 joules. We also know at the start, kinetic energy is equal to 0. So our total energy is 9.8 joules. So at 7 meters, we'll have 0.1 kilograms times 9.8 meters per second squared times 7 meters, which is 6.9 joules. 9.8 joules minus 6.9 joules will give us the remaining energy as kinetic, which will be 2.9 joules. At 3 meters, 0.1 kilograms times 9.8 meters per second squared times 3 meters is 2.9 joules. The remaining energy will be kinetic at 6.9 joules. And at 0 meters, it will be 0 joules of potential energy and thus 9.8 joules of kinetic energy. The total energy is kinetic energy plus potential, so the kinetic energy is total energy minus potential. What we will be doing is measuring, in the lab, we'll be measuring kinetic and potential energies and seeing the total is vaguely the same. There's a lot of errors when we actually do this in the real world in the lab, because we're not measuring very well. So that's fine. And there's losses. So height 10 meters, total energy is 9.8, potential energy is 9.8, kinetic energy is 0. 7 meters, total energy is still 9.8, potential energy is 6.9, kinetic energy is 2.9. 3 meters, total energy is 9.8, potential energy is 2.9, kinetic energy is 6.9. And last at height 0, total energy is 9.8, potential energy is 0, kinetic energy is 9.8. You can see as potential energy goes down, kinetic energy goes up. Potential energy is transformed into kinetic. And you can have the opposite happen as well. So if you want to figure out the magnitude of the velocity, potential energy converted is mg change in height. This is converted into kinetic energy, 1/2 mv squared. Since all the potential energy is converted into kinetic energy just before hitting the ground, we can use this to compute the speed or magnitude of velocity. Therefore, 1/2 mv squared equals mgh, mass cancels, and 1/2 v squared equals g times delta h. V squared equals 2g delta h. Velocity is the square root of 2g delta h. That's a useful problem if you have something starting at rest. Its final velocity will be 2g times this change in height, as long as there's no friction. So here's a problem using that. We have a 25-kilogram child going down a 3-meter tall slide. What's the kinetic energy of the child at the bottom of the slide? And what's the speed of the child at the bottom of the slide? So remember, kinetic energy plus potential energy at the start equals kinetic energy plus potential energy at some later time. And kinetic energy is 1/2 mv squared, potential energy is mgh. With a 3-meter tall slide, you can set 0 meters to be the potential energy at the bottom, 3 meters to be the height at the top, and calculate the potential energy from there. So potential energy plus kinetic energy at time 1 equals potential energy plus kinetic energy at time 2. But at the top of the slide, the child isn't moving. So we can cancel initial kinetic energy. And at the bottom of the slide, well, that's the bottom. That's height 0. So there's no potential energy. So this simplifies to just potential energy 1 equals kinetic energy 2. Wow, I crossed those out twice. I gotta clean that slide up. So mgh is your initial potential energy, which is also going to be your final kinetic energy. So 25 kilograms times 9.8 meters per second squared times 3 meters, or 735 joules. That's the answer to part A. For part B, well, now we know what the kinetic energy is. Kinetic energy is 1/2 mv squared. So v squared is 2 times kinetic energy over mass. So the square root of 2 times kinetic energy over mass is going to be the velocity. So 2 times 735 joules over 25 kilograms gives us 7.67 meters per second. You could also do this with square root of 2g delta h, 2 times 9.8 times 3 meters, take the square root, you'll also get 6.67 meters per second. Both of these work, but because I asked for the kinetic energy first, it's easier to just sort of continue on. So we have a 1 kilogram ball traveling at 3 meters per second, and it rolls up a ramp. How high has the ball traveled up the ramp when it comes to a stop? So it starts with some kinetic energy and rolls up a ramp, turning it into potential energy until it has none left. So I'll let you guys think about that for a bit. So in your initial case, you only have kinetic energy, and in your final state, you only have potential energy. So 1/2 mv squared equals mgh. We can cancel mass and solve for h. We divide both sides by 1/2 m. We divide both sides by mg, sorry. And we get height equals v squared over 2g. So h equals 3 meters per second squared divided by 2 times 9.8 meters per second squared, which is 0.459 meters. I apparently made a mistake when typing it into the calculator. Hit the wrong key. The 0.459 meters. So here we have a 1,000 kilogram car traveling at 2 meters per second, rolls down a 4-meter high hill. What is the speed of the car at the bottom of the hill? So this car starts with both potential and kinetic energy and ends with just kinetic energy. So here, only one term will go away. So we start with mg some height plus mg some initial velocity squared. And that will equal 1/2 mass times some final velocity squared. Well, the first thing we can do is we can divide through everything by mass if we want to. And it also helps to multiply everything by 2, just to get rid of the 1/2. So we end up with 2gh plus v initial squared equals v final squared. So v final is going to be the square root of 2gh plus v initial squared. So 2 times 9.8 meters per second squared times 4 meters plus 2 meters per second quantity squared. So that's 78.4 meters squared per second squared plus 4 meters per second squared, which is 82.4 meters squared per second squared, which is 9.08 meters per second is the final velocity. And with these simple kinetic and potential formulas, mass will always cancel out, which is one of the nice things. There are other ways to have potential energy. So like if a spring is involved, mass will not cancel out. But in these cases, it does. With gravity, it does. So how fast does a 300-kilogram roller coaster car need to travel to be able to roll over a 20-meter high hill? So here, you start with some velocity, and you need to have enough kinetic energy to just have no velocity at the top to make it over. That'll be your minimum speed. Now, in actuality, you'd like to have more than that, but that would be your minimum. So, in this case, we start with no potential energy, but some kinetic energy, and we end with some potential energy and no kinetic energy. So 1/2 mv squared equals mgh. Mass will cancel. We divide everything by 1/2 mass. We get v squared equals 2gh. V equals the square root of 2gh. We're really just doing the rolling down the hill formula backwards. But backwards in time. So now we're rolling up the hill, but we're trying to find how fast we need to go. And that's as fast as we would be if we rolled down the hill. So 2 times 9.8 meters per second squared times 20 meters. Square root of 392 meters squared per second squared, which comes out to 19.8 meters per second. you're actually shooting a roller coaster over a hill, I'd want at least 20. So here we have a pendulum. If we have a 2-kilogram pendulum bob, it started swinging at a height 10 centimeters above the bottom point of the swing. So what's the speed of the bob at the bottom of the swing when its height is dropped by 10 centimeters? And how high will the pendulum bob reach on the other side of the swing? So there are 3 states here. There's our initial state at the bottom and then up at the other side. And we can work out potential and kinetic energy for all of these states, and the total energy will be the same for all of these states. So for part A, we know that we start with potential energy and no kinetic energy. And at the bottom of the swing, we have no potential energy and only kinetic energy. So mgh equals 1/2 mv squared. V squared equals 2gh. V equals square root of 2gh. So square root of 2 times 9.8 meters per second squared times 0.1 meters. The velocity comes out to 1.4 meters per second. Here is the extended version of this for all 3 positions. We start with potential energy and no kinetic. Then we get to the bottom where we have no potential, only kinetic. And then we get to the top. We get back up on the other side where we only have potential energy and no kinetic. So we have mgh1 equals 1/2 mv squared equals mgh3. We don't care about the middle. For part B, we're interested in h3. So h1 will equal h3, which will equal 10 centimeters. It's going to go to the same height it went up to. It started out on the other side, assuming there's no friction. Now, in reality, there is friction, and so it'll be slightly lower, but we're going to ignore that. So we have a bit more time. So I will go over a bit of the theory for the start of the next section, which will be the end of chapter 4. So we talked about kinetic potential energy, conservation of energy, conservation of mechanical energy, so power. So this is going to introduce a unit you're probably familiar with. So power is a measure of work over time, the rate of doing work. The power is work divided by time, or force times distance over time. And the SI unit is a joule per second, and it's called a watt, after James Watt, who improved the steam engine and also invented a unit of power. So a 100-watt light bulb uses 100 joules every second of electrical power, 100 watts. And be careful not to confuse work with watt. One is a unit, one is a variable. So if you use a force of 1 Newton to raise a mass 1 meter, the amount of work done is 1 joule. If this is done in 1 second, then the power is 1 watt. So the SI units, the unit for force is the Newton. It is a kilogram meter per second squared. The unit for work is the joule. It is a Newton meter, or a kilogram meter squared per second squared. Energy is also the joule, and power is the watt, which is a joule per second, which is a kilogram meter squared per second cubed. No one wants to write that out. And you've probably seen things rated in watts for electrical devices. Turns out, if you have an electrical device with, you want to figure out how much power it uses, you can actually just multiply the current times its voltage. That will give you power. That has to do with the definition of what voltage is, because voltage is related to energy, and current is related to how much electrical charge, and voltage is sort of energy per unit charge kind of thing. So when you combine them, you get energy, you get power. Now, the unit of power in the British system, well, the unit of work is the foot-pound, and so power is the foot-pound per second. Now, a more commonly used unit of power is the horsepower. The horsepower was invented by James Watt to sell steam engines, which is why it does not nicely or in any simple way correspond to the power output of a horse. The nominal description was it was supposed to be sort of the average power output of a horse over a long period of time, including rests and stuff. But like, I have seen an experiment where they hooked a horse up to a dyno and it put out 6 horsepower. It's going to vary from horse to horse, but it also depends on how much time you're doing it. But a horsepower is defined as 550 foot-pounds per second, or 746 watts. There's also a metric horsepower, which is exactly 750, I think. I don't know. The horsepower is messy. But for this, it's 550 foot-pounds per second, or 746 watts. And the greater the power of the engine, the faster it can do work. So a 2 horsepower engine can do twice as much work as a 1 horsepower engine in the same amount of time. So a constant force. So, nominally the idea of a horsepower was that if you had a 3 horsepower engine, it replaced 3 horses. That was that was their selling point. But again, this is a unit that was created to sell steam engines. So if you have a constant force of 150 newtons that is used to push a student's stalled motorcycle a distance of 10 meters along a flat road in a time of 20 seconds, we want to calculate the power in watts. Force is 150 newtons, distance is 10 meters, time is 20 seconds. So power is work over time, which is force times distance over time. So 150 newtons times 10 meters over 20 seconds, 75 watts. One of the nice things you might see is that this has distance over time in it. That's just speed. So if you're using a constant force to keep a constant speed or a constant velocity, power is just force times velocity. So here, a student expends 7.5 watts of power lifting a textbook half a meter in 1 second. How much work is done and how much does the book weigh in newtons? So to figure out work, you're going to take power times time. Work is power times time. So 7.5 watts times 1 second, that's 7.5 joules. Weight is a force. Work is force times distance, so force is work over distance. So 7.5 joules divided by 0.5 meters, that's 15 newtons. So the work done is 7.5 joules, and the book weighs 15 newtons. Now, for electrical energy use, power is the energy produced or consumed over the time. So the energy is power times time. Power is given in watts. Power times time would be in joules. So our units of work or energy is joules. However, that's not how we sell electrical power. We sell electrical power in kilowatt hours. And a kilowatt hour is a kilowatt, 1,000 watts, times an hour, 3,600 seconds. So 1 kilowatt hour is 3.6 megajoules. Because it's 1,000 times 3,600. So we could buy our electricity in megajoules. That would probably look much cooler on your electric bill, but we don't. We buy it in kilowatt hours. Part of that was probably was easier to meter kilowatt hours early on, because you could set up something that moved in a rate proportional to. There are ways to do it. Basically, the way that the electric meter works is that the speed it rotates at is determined by how much power you're using. And so how far it's gone is determined by how long it's been moving at that speed. So if you were using a kilowatt of power, it would move at a rate where in 1 hour it would move 1 tick. And it's probably easier to calibrate that in kilowatt hours than in megajoules or whatever. But yeah, we use kilowatt hours. 1 kilowatt hour is 3.6 times 10 to the 6 joules. 3.6. So if you have a 1 horsepower electric motor that runs for 10 hours, how much energy is consumed in kilowatt hours? So power is 10 horsepower, time is 10 hours. So we're going to need to convert power from horsepowers to watts to kilowatts. Well, 1 horsepower is 746 watts, or 7.746 kilowatts. And then we're going to multiply that by 10 hours. So 0.75 kilowatts times 10 hours is 7.5 kilowatt hours for 2 significant figures. It'd be 7.46 kilowatt hours rounded to 7.5. So power is work over time or energy over time. So energy is power times time. And I think I will stop there for today. We'll go over this again on Wednesday. And you know, I'll work on. I should have your quizzes graded by Wednesday. I don't, and they will probably be on the midterm grade, because the midterm grades are due Wednesday morning. I haven't figured that out yet. But the midterm grades will be on Wednesday. Will be turned in by Wednesday morning, probably before then, because I'm going to get them done tonight.